Good morning. Today we are going to present our project about the simulation and the serious games. And we are Regina Mujica Limón, Isabel Aguilar Mijares, and I am Daniela. So we can start with the presentation.
The objective of this project is to use our knowledge of the Newton's laws, the application of derivatives, the use of MATLAB, and the cinematic formulas to create a simulation of a parabolic movement of a projectile. This is important to calculate a more precise landing point, as we do in serious games, to give a team of rescuers a precise knowledge of the event and a better chance at saving lives.
Okay, for making our simulation, it was important to note that a volcanic eruption happens when pressure builds up inside the earth and pushes a hot melting rock called magma. The lava can destroy plants, animals, and buildings. Ash and gases spread in the air, making it hard to breathe, and sometimes even block sunlight, and this causes changes in temperature. Also, we need to investigate what are serious games. Serious games are interactive apps that work like video games, but their main goal isn't just fun. They are meant to reach and train professionals, but they still include fun parts, challenge, and stories to keep players engaged while they are still learning. Some serious games that are used in real life are Children's Safe Hearts, which is for teaching children basic life supports, and also Merit, which is for training paramedics in for emergency situation, and they train for how will they react and how much time will they take for solving some problems.
After this research, we started doing our simulation without a resistance first in an Excel file. Following the formulas, we obtained these four graphs of position, velocity in y, and in the x-axis, and the acceleration. As we can see in the position one, the values along the x-axis continue increasing in a constant rate in the ideal way because we're not implementing a resistance. So we can see a somewhat symmetrical parabola, while the values in the y-axis arrive to a maximum point and then start going down until it reaches to zero once again, which is the ground. Then in the velocity along the y-axis, we see that it starts in a positive value and then starts decreasing till it reaches to zero. That is when the parabola hits its maximum height, and then it becomes negative, which means that the parabola or the projectile started moving downwards. As in velocity in the x-axis, it is always remaining constant as of initial velocity because of what the cinematic formula of velocity states. As well as the acceleration, it is always constant and it's equal to the negative of the gravity, which is minus 9.8. The formulas that we used to calculate this past graphs were in position, x is equal to the initial position plus the velocity in x times the time. Y is equal to the initial position of y plus the velocity in the y times the time minus half multiplied by the gravity multiplied by the time squared. In initial velocity, we used to decipher the components of initial velocity, we used for x initial velocity, the cosine of theta, and for y, initial velocity, the sine of theta. This was needed to calculate the velocities, which was velocity in x is equal to the initial velocity, and velocity in y, it's equal to the initial velocity in y minus the gravity times the time. And acceleration, it's equal to the minus gravity. We can also see if we want to calculate the horizontal range, the time to maximum height, and the time it takes in total flight, it's these other three formulas, which all have to do with velocity and gravity.
Air resistance was added by including terms that depend on velocity. This means the faster the object moves, the more the air pushes against it. Because accelerations keep changing, we use a numerical method called Euler's method to update the motion step by step. As a result, the object path becomes lower, shorter, and less even than it will be without air resistance in the ideal case that we previously saw. These formulas show how air resistance affects the motion of an object, in this case, sometimes like volcanic ash or rock ejected during an eruption. Acceleration formulas tell us how the speed changes over time. The term b between m show how air resistance slows down the object. Velocity formulas show how fast the object moves in the x and y directions. Air resistance makes it lose speed as it moves. Position formulas help us find where the object is in any moment, how far it travels horizontally, and how high it goes before falling back down. The letter means B, air resistance, M for mass, G for gravity, and time, and T for the time interval. This is like, imagine a piece of rock flying out of a volcano. At first, it moves fast, but as it goes higher, air pushes against it. That's air resistance. These formulas help us predict how far and how fast that rock will go before falling into the ground. Here we can see the comparison between the simulations with air resistance and without air resistance. For position without air drag, we can see that the graph shows a perfect parabola. With air drag, the trajectory is shorter and asymmetrical, showing how air resistance will reduce height and range. For velocity next, without air drag, we can see that remains constant, forming an horizontal line that shows there is no horizontal acceleration. With air drag, on the other hand, it starts and gradually decreases to zero. The speed decreases faster at the beginning because air resistance, as I said before, is stronger at higher velocities. Velocity in y, without air resistance, goes down in a straight line, decreasing every second. By with air drag decreases faster at first, reaches zero, and then slows down more gently because air resistance reduces the speed change. Acceleration is next. We can see that without air drag, there is no horizontal acceleration because without resistance, there is no an horizontal force. But with air resistance, the graph starts with a negative acceleration and slowly moves towards zero. This means that the air drag force becomes weaker as the projectile slows down. For acceleration in y, without air drag, we can see that it stays at the same, which shows a constant pull of gravity. And with air drag, it starts very low, then goes up, passes zero, and ends high and positive, showing that air resistance changes the acceleration during flight.
Now we are going to present the simulation in MATLAB.
The logic with which we made this MATLAB simulation and project was first selecting our buttons and starting our function, define the parameters, create the arrays that are going to store the values so we can have different points along the trajectory as the Euler's method states, start the while loop to create set points, calculate the positions and the velocity, update the values and enter them into the arrays that we created, end the while loop, plot the figure, create a volcano triangle, after that create a lava triangle, and we end the program.
And on this slide, we can see the entire model for the projectile movement. The movement was modeled by using a numerical simulation based on Euler's method. This approach calculates the projectile path step by step. In a while loop that runs as long as the height, y, is above zero. At each time step, the dt, the simulation updates the projectile's velocity and position. The model incorporates gravity, which means the g, and the air resistance or the air drag, which is b divided into the mass and multiplied by the velocity, where b is the air drag. And also we have the scalars, which are constants like initial velocity, launch angle, the mass, the drag coefficient, and the gravity are stored as scalar numerical values. We have the rays. The projectile's path is stored into the dynamical growing arrays, which are the vectors, x and y in each loop. The new x mu1 and y mu positions are appended to these arrays. The trajectory is visualized using the plot function to draw the x and the y arrays on the y-axis. Creating the red line and then fill the function is used to draw two small polygons at the origin, creating the brown volcano and red lava for the visual context. And in our final simulation was a MATLAB app. It models the trajectory of a projectile launched from 0.0 with a set of predefined physical parameters, including an initial velocity, the angle, and air drag coefficient. The user interaction is pushing the click to start, which is this. When the user press that, the function starts running, and we can see the simulation. The simulation displays the projectile complete journey as a single 2D motion plot of height versus horizontal distance, which appears after the simulation finishes. While the code calculates the speed and position values at every time step, it does not display these as updating numbers. The primary result shown to the user is the final path graphic on the x-axis.
The findings and results that we saw in comparison to the trajectory with and without the air resistance is, well, the most obvious one is the shape. As you can see, the first one looks more symmetrical and it goes up and falls with the same angle. As for the second one, it looks way flatter, goes up a little bit more steeply with an angle smaller than 45 degrees, and you can see that it falls down almost vertically. The range, like you can see in the numbers, without the air resistance, it travels farther because there's nothing stopping it or like obstructing it. like it is with the air resistance, that it has a much shorter range. This is also applied in the time of flight, because it travels a much farther path. It takes way more time to complete its flight and depends only on the initial velocity and the y and the gravity. As in with air drag, it has a shorter time of flight, given that the air resistance reduces the velocity.
Conclusion is that we were modeling the trajectory of the volcanic projectiles, a critical factor in developing serious games, which are used for rescue and training. The simulation demonstrates that accounting for air resistance or ATRAC is essential for accurately predicting the landing zones of volcanic ejecta, providing rescuers with more precise knowledge to save life.
Thank you so much for your attention.